In the previous chapter, we looked at how we could form alkenes through an elimination reaction. In this chapter, we're going to take alkenes and we're going to add things across the double bonds that alkenes have, essentially doing the reverse of an elimination reaction. So there's lots of ways that we can go with this. There are lots of things you can add across your double bond. And the key thing, though, is realizing that essentially whatever you're adding, you're splitting it up into two parts and adding each half to your carbon of your double bond. Okay, so if you can keep that in mind, that probably makes organizing this information or compartmentalizing it a little bit easier. Okay, so this table here kind of just breaks down the different types of addition reactions we're going to look at. But you can see that what they all have in common is that we are adding two halves of something to the two carbons of our alkene. Okay, so basically what alkenes have that's kind of reactive here is the pi electron, or the pi electrons from their carbon-carbon double bond. Okay, so we've seen before that these pi electrons can act as a base and as a nucleophile. Essentially, those electrons can be donated to either a proton to act as a Lewis base or to some sort of electrophile. Okay, and that's essentially how we form a bond with said, proton or electrophile. As a result, we get a carbocation on the other carbon of our carbon-carbon double bond. Okay, so essentially that's what kind of picks up the other half of the molecule here. So for example, if we do a hydrohalogenation here, we can add this hydrohalogen. So we add a proton here to one carbon, and the resulting carbocation adds on the halide ion, and that gives us this corresponding alkyl halide. Now, if that looks familiar, you'll remember that in the last chapter we saw that doing an elimination reaction across these two carbons, so essentially you remove this halide as a leaving group, and then we've got this beta proton that gets removed as well. That forms a double bond across those two carbons, which forms the alkene that we started with in our addition reaction. Okay, so think of these as kind of two processes that make this a reversible reaction, and as a result, you've got to consider that these two reactions exist in an equilibrium. Okay, so as such, we can look at this from a thermodynamic standpoint. Okay, so using our Gibbs free energy equation, remember that delta G is equal to delta H minus T delta S. Okay, or here it's organized with our T delta S, negative T delta S as a single term. Okay, so let's look at the forward reaction here. So let's look at that addition reaction with our alkene reacting with a hydrogen halide to make our corresponding alkyl halide. Okay, so first let's look at the enthalpy involved. All right, what bonds are we breaking and what bonds are we forming? Well, in our alkene, we're going to break this pi bond here, and we're also going to break the sigma bond between our hydrogen and our halogen. To make our products, we're forming two sigma bonds, a carbon-hydrogen bond and a carbon-halogen bond. Okay, so notice again, we're breaking a pi and sigma bond, but we're forming two sigma bonds. So it should come as no surprise to you then that the energy that's released from forming these two sigma bonds is going to be greater than the energy required to break your sigma and pi bond. So it should therefore come as no surprise then that this is going to be an exothermic process. Your delta H is going to be a negative number for your addition reaction. Okay, so that's pretty typical. All right, so that's something to keep in mind then for that delta H term in our Gibbs free energy equation. Okay, now what about delta S? Well, for delta S, you want to think about how entropy for this reaction is going to change as you go from your two reactants to your one product. Okay, so think about that, right? You're going from two reactants, which have more degrees of freedom, and they're now stuck together as one product. That's a decrease in entropy. So delta S is going to be a negative term. But remember, delta S is tied into this term here with negative T. So overall, this term is going to be positive for your addition reaction. So now you should realize then that you have a conflict. All right, our negative enthalpy term is in conflict with our positive entropy term for the addition reaction. Obviously, for that reverse reaction, for the elimination, this is backwards, right? So if we want to favor our forward reaction, the addition reaction, how can we do that? Well, remember, we want a negative delta G for this process, right? That's what makes a reaction spontaneous. So if delta H is negative, how can we make this entropy term, okay, which is positive, less important, okay, and therefore not capable of overcoming that enthalpy term? Well, that's where temperature comes in, right? If we have a lower temperature, this term becomes smaller. So essentially, your addition reactions tend to occur at lower temperatures. Okay, so here, for example, we have an addition reaction between this alkene and hydrogen bromide, and we can see that in doing so, this reaction runs best at negative 30 degrees Celsius. Okay, we get a relatively decent yield of product at that low temperature. Okay, quick note on this sort of question down here. Notice that our reactant is symmetrical here. So which side that gets the hydrogen, which side gets the bromine actually doesn't matter, right? If we got the bromine on this side, it would be the same molecule just flipped over. However, I do want to point out that this is something we're going to pay attention to quite a bit in this chapter. So just a little preview of what's to come here. Okay, so like I said, the regiochemistry is going to be kind of important for distinguishing like what products we make. We want in that previous example we had a symmetrical alkene, so it didn't really matter. But if we have an asymmetrical alkene, we need to know which type of product we're going to make. Are we going to get a mixture of products? Well, it turns out that we actually have a preference for one product versus another. Okay, and this is called the sort of rule that governs it is known as Markovnikov's rule, named after the scientist who kind of showed it or explained why it happened. So Markovnikov's rule is that when you're adding a hydrogen halide to an asymmetrical alkene, the hydrogen goes to the carbon of your double bond that has more hydrogens on it. Okay, your halogen winds up on the more substituted carbon of your double bond. Okay, so you want to think about why this happens. So there's going to be a mechanistic explanation for this that we're going to see in a second. Okay. Oh, a quick note here. It is possible to get the anti-Markovnikov product, so to speak, where here we can see where the bromine's added onto the less substituted carbon. Of course, in order for this to happen, to get this in a larger quantity, we're going to have to change our reaction conditions quite a bit. Okay, we'll see that over in chapter 11 because that's going to involve a radical reaction. Okay, so we'll see that in chapter 11.10. Okay, so so we call that the anti-Markovnikov addition. We'll get into that later, but essentially you'll find that it helps to have a source of radicals such as this peroxide here, if you want to make that anti-Markovnikov product. Okay, so let's talk about this hydrohalogenation mechanism and see why is it that Markovnikov's rule takes place. All right, so the first thing to happen is a proton transfer. Your alkene acts as a Lewis base and picks up the proton from your HBr. Okay, I guess you could say it's it's donating those electrons to the proton. So it's acting like a Lewis base, though I guess you could also see this from a Bronsted-Lowry standpoint and see that it's picking up the proton from your HBr. Okay, so regardless, it's acting as a base. It's doing the proton. It's doing the proton transfer, picking up a proton. Now, when it picks up the proton, you've got two options for which carbon can pick up the hydrogen. Now, if the carbon on the right picks it up, notice that we form a tertiary carbocation here. What would have happened if this carbon on the left had picked up that proton? Well, this carbon over here has only two carbons attached to it, so this would have been a secondary carbocation. So out of your two potential carbocations, you can see that this one is more stable. Okay. Now, of course, you've got this carbocation, and you've got this negative bromide, which is a good nucleophile. It does its nucleophilic attack on that carbocation and produces the product that we see. Okay. Notice, by the way, again, that this is the two steps of an E2 mechanism, or sorry, an E1 mechanism, just in reverse order. Okay. All right. So here's the reaction coordinate diagram showing this two-step process. So you can see here that slow step involves that proton transfer, that kind of that formation of that carbocation is the rate determining step there, which kind of makes sense. That nucleophile is going to quickly attack that relatively reactive intermediate carbocation and produce your product. Okay, so again, this kind of highlights why we see a Markovnikov versus anti-Markovnikov product. So notice that when our proton gets added to our less substituted carbon, our carbocation has more substitutions. And remember, the more substituted your carbocation is, the more stable it is due to the hyperconjugation of those carbon-hydrogen bonds sort of donating into that MTP orbital. Okay, so if you want a refresher on that, go back to where we first started talking about carbocations. You see that if the hydrogen adds to the more substituted carbon, okay, so it adds to this carbon on the right, notice that here we only have a secondary carbocation. So the potential energy of this intermediate is much higher than the potential energy of this intermediate. Okay, so from a kinetic standpoint, the activation energy to make this and have it react is going to be much lower than for this intermediate. Okay, so there's a kinetic argument to be made here. Okay, and so here's the visualization of that. Notice that our tertiary carbocations at a much lower, has a much lower energy. Okay, actually, I guess our carbocation's over here, but as such, it has a much lower activation energy, and therefore it's much easier to form that carbocation, and therefore you get more product from that carbocation. Okay, now another thing to watch out for, besides just your regiochemistry, you also have to watch out for stereochemistry regarding chirality. Okay, so sometimes when you have your halogen added on, this is a different atom, a heteroatom that really helps form a chiral center sometimes, depending on what other groups are on that carbon. Okay, so you can see, for example, here when we add that chlorine, notice that we have a methyl group, an ethyl group, a chlorine, and a hydrogen. Okay, that hydrogen wasn't shown, but there was already a hydrogen here. Okay, so where that chlorine adds can give you two possible products. You could have the respective R or S enantiomers depending on which side that chlorine adds onto. Okay, so what side does that chlorine add onto? Well, where is the chlorine adding to? Why, you're starting off with a carbocation, which remember is flat, it's trigonal planar. So the chlorine can add to either side. Okay, so it's actually relatively easy to form either an enantiomer. So you actually get a racemic mixture of products. Okay, but something to keep in mind when you're predicting your products for these addition reactions. Okay, now because we're going through a carbocation intermediate, you want to consider that sometimes there are carbocation rearrangements. Okay, so it is possible, for example, when if you have your hydrogen add on here, okay, and so you're going to make this secondary carbocation as opposed to the primary one if you had the positive charge on this side. But even with this secondary carbocation, it's possible to do a hydride shift. We have this hydrogen shift over, and now we've made a tertiary carbocation. Okay, now our halogen, our halide nucleophile, is going to attack that tertiary carbocation to give you this product, which is going to look different than if it attacked this secondary carbocation. So this is actually going to be your major product here, and that's something you need to keep in mind when you're predicting the products of this reaction here. Okay, so it's not enough to just think, okay, H goes to one of these things, Cl goes to the other of these things. You've got to think about the whole mechanism sometimes. Okay, so something to watch out for. So notice that here our rearrangement product makes up the majority of our product. Okay. So with that in mind, let's try a practice problem out. Okay. So ask yourself, what will the carbocation for this look like? And then accordingly, what will the resulting products look like once the chloride ion adds on to it? Okay, so this one's going to be kind of interesting to draw here. Out of these two carbons, your hydrogen's going to add to this one on the left because that's less substituted. And so you'd form your tertiary carbocation over on this carbon here. Now your chlorine's going to add to either side of it, and as a result, you're going to get two different products. Okay, so accordingly, your chlorine's going to be either sort of axial or equatorial here, and accordingly, it's going to force this bridge of your bicyclic compound up or down. Okay, so something to keep in mind just for from a sort of 3D perspective. Again, this is kind of, don't stress too much about problems like this. Is going to be a little bit tougher than something you would see on an exam. But this is kind of what it would look like. So let's say we sort of kept this geometry here. So in other words, the chlorine added down here. And so that keeps this sort of kind of equatorial. And so we have a axial chlorine, I'm just going to draw it this way, pointing downwards. But just realize that we could also have a, we could have a molecule that looks like this, right? And essentially kind of have our chlorine sticking out here and have this bridge sort of being down at the axial position, okay, or something like that. So anywho, something to consider, but don't stress too much about the difficulty of this problem. Okay, but that's sometimes it's good to sort of think of what this might look like in 3D. And if you're having trouble seeing it, of course, just build a model or something. Okay, so in the previous section, we talked about the addition of a hydrogen hydrohalide, right? We added a hydrogen and a halogen across our double bond. In this next section, we're going to look at hydration reactions. As the name suggests, we're adding a water molecule across our double bond. So in other words, we're adding a hydrogen to one carbon and an alcohol group to the other carbon. Okay, the two of those combine to make H2O, or water. Now, just because it's called a hydration and we're effectively adding a hydrogen and an alcohol group, doesn't necessarily mean that they come from the same water molecule. Okay, we're actually going to do this, depending on the reagents we use, we might not use water directly, actually, to do this. So the simplest way to have this reaction occur is to do this in the presence of water, but using an acid catalyst. Okay, so the thing that sort of initiates this is the addition of that proton transfer step that we saw with our hydrohalogenation is still a good first step to do here with a hydration reaction. And so having an acid present really encourages that step. Okay, so you'll find that oftentimes sulfuric acid is a very useful reagent here. Okay, now this is we call this a catalyst because the sulfuric acid itself is not a reactant. It doesn't actually get used up, so to speak. The protons that it provides eventually get regenerated. Okay, you get the sulfuric acid getting regenerated again. It's the water molecules that wind up effectively getting added across. Okay, so we'll see the mechanism of that, and you'll see what I mean. Okay. Oh, quick note here though, we're still following Markovnikov's rule when it comes to this type of hydration reaction. Notice that our hydrogen added to our less substituted carbon, and the alcohol group added to the more substituted carbon. Okay, so it's the same Markovnikov's rule that we saw with our hydrohalogenation. Okay. So, if we look at the substitutions on our carbon, okay, notice that the more substituted our carbon that gets the alcohol group, the faster the rate. Okay, so that should tell you that this probably goes through a carbocation, right? Because clearly this tertiary carbocation was stable enough to really rapidly increase the rate. So let's look at that mechanism. Well, it's pretty similar to the one we saw before. We have our proton transfer step, where our alkene picks up a proton from the hydronium that's floating around. Okay, and then with the resulting carbocation, a water molecule will attack that. Okay, so that oxygen acts as our nucleophile. Okay, the lone pair on the oxygen acts as a nucleophile, and we get the resulting oxonium ion, that's essentially the alcohol, but it's protonated, and we want to deprotonate that to make our neutral oxygen, okay, and therefore make the stable alcohol. All right. So you can see again what I mean by the water not strictly being added across directly. This hydrogen over here came from a hydronium ion, and this water molecule was a completely different water molecule that gave us the alcohol group. Okay. Note, by the way, that this proton that gets plucked off over here is what regenerates your acid. Okay, and this is why the acid is considered to be a catalyst. Okay. All right. This last question over here is kind of silly, right? Would you want to use a stronger base than water to do this? The answer is no, right? Because remember, you're doing this in the presence of a strong acid. If you have a strong base present, it's going to use up your acid, and there goes your catalyst. All right. So, again, this is still going to be an equilibrium that you've got to deal with. We're looking at this addition of water across this double bond, but keep in mind that this this alcohol, in the presence of an acid, is going to undergo the elimination reaction to go back to forming your alkene. Okay, so remember, in the presence of an acid, if you protonate that alcohol, it's a good leaving group. Okay, and you're going to do that elimination reaction. So, how can we force the addition reaction as opposed to the elimination? How can we drive this reaction forward? Well, we've already seen how temperature can do this. We can use a low temperature to kind of encourage the addition reaction. And you can totally do that. But keep in mind, by the way, that low temperatures aren't great necessarily for reaction rates. Just from a kinetic standpoint, right? Your molecules have less average kinetic energy and a lower average, and therefore you have fewer successful collisions, right? So what else could we do to encourage the equilibrium to get shifted to the right here? Think Le Chatelier's principle. Okay, notice that we have water here as a reactant. So if you have more water, that's going to push this equilibrium to the right. So using dilute sulfuric acid will encourage that addition reaction. Using concentrated sulfuric acid will encourage the reverse reaction. Okay? So something to keep in mind there, using just something you learned back in Gen Chem. Okay, Le Chatelier's principle could be useful here. Okay, so regarding stereochemistry, again, if you want to, you've got to watch out for, depending on your substrate, when that alcohol group adds on, it might be a fourth group that makes a chiral center. So keep in mind that you're going to get a mixture of products. Okay, you're going to get a racemic mixture because again, that alcohol group is adding on to a carbocation, and carbocations are trigonal planar. Okay, so that alcohol group could add to either side. Okay. So just as a reminder, here's the full mechanism of the formation of this product, and here's that trigonal planar carbocation I mentioned. Okay, so when your water molecule comes in to eventually form your alcohol group, it attacks either side of that carbocation, and therefore you get the enantiomer as well as the molecule shown over here. Okay, so by the way, if you want to, if you're ever drawing these mechanisms out and you don't want to have to draw both enantiomers, it's understandable if you just say plus enantiomer. Okay, so yeah, let's look at another example here. So here we have this alkene, and let's again we're going to do a hydration reaction using a dilute acid. So let's go ahead and predict the product for that reaction. So you probably noticed that the this is not a symmetrical alkene, right? We've got, if our hydrogen adds over here, this will make a tertiary carbocation, whereas if the hydrogen adds here, we'd only get a secondary one here. So your alcohol group's going to add onto this side. Okay. Now notice that again, this is also not a symmetrical one from a stoichiometry standpoint. That this is going to be a chiral center. You've got a methyl group, a hydrogen that's, or actually the alcohol group you're adding, and then of course this pathway and this pathway are different. Okay, notice you've got one carbon and then a second carbon in a methyl group. Here you have to go through two carbons before you get to the carbon with the methyl group. Okay, so that this carbon is going to be chiral once you add an alcohol group there. Okay, so your products are going to look like this. So you have your alcohol group, or your methyl group here, sorry. It's drawn kind of lousily. And of course, your alcohol group could either add on top here and force this methyl group to point downwards, or that methyl group, or that alcohol group, sorry, could add from the bottom, causing that methyl group to point towards you. Okay, so there's your two products for this reaction. Okay, now using concentrated sulfuric acid is not necessarily the only way to make a hydration product, to make an alcohol by adding across a double bond. Okay, there are other methods that we can use, and we sometimes consider them for the different just stereochemistry considerations. Sometimes you want to be careful from just a mechanism standpoint. You're using sulfuric acid, you're going through a carbocation intermediate. Well, due to rearrangements, that might cause some products that you don't want. Okay, you might get some some byproducts, and that'll lower your yield, right? Or you just might, you want the product that's not the rearrangement product, right? So we've got to consider other ways to make that Markovnikov addition. We're also going to look at ways to do an anti-Markovnikov addition as well for these hydration reactions. And I'll get into that in a second. The first of these alternative ways to do a hydration is the oxymercuration-demercuration reaction. Okay, so basically we're going to make the Markovnikov addition product, but we're not going to have to worry about a rearrangement occurring. Okay, so that's a nice convenient thing about this. So in the oxymercuration step, we essentially add on a mercury acetate group as well as our alcohol group, and then of course in the demercuration step we get rid of that, the mercury part of it, to leave just the alcohol. Okay, and notice that again, from our double bond, our alcohol has added to the more substituted carbon. Okay, so that's following Markovnikov's rule. So how do we do oxymercuration? Well, we start off with mercuric acetate, or mercury 2 acetate. Okay, and so if we kick off one of those acetate groups, we are left with the corresponding cation with our mercury. Now, of course, that's going to be a great electrophile, right? And so you can see where we're going with this, right? We have our alkene, which is a great nucleophile, right? It's going to seek out this positive charge. So we can see here it's going to attack, it's going to do that nucleophilic attack on our cation here and form the corresponding complex, this mercurinium ion. Now, this mercury actually winds up coordinating kind of to both carbons. It kind of interacts with that carbocation here and just stabilizes it a little bit more. Okay, so that kind of also, it puts the positive formal charge on that mercury, which being a metal is okay. So that kind of actually brings down the activation energy for this process. Okay, so this is kind of the hybrid of what that looks like. All right, now you then have your nucleophile coming in, okay, and that attacks your carbocation, okay, and adds on to, so it again, out of the, in your mercurinium ion, the partial positive charge is more stable on this more substituted carbon, right? So there's a little bit more of a partial positive charge here, and that makes it more prone to your nucleophilic attack. All right. So even though you kind of have this hybrid where both carbons are taken up, there is a preference for your nucleophile to come in and attack that more substituted carbon, and that's why you get the Markovnikov product. Okay. So anyway, this is a great electrophile. So even a weak nucleophile like water is going to attack this. Okay, and that's kind of what happens, right? You add a water molecule, which you can then deprotonate to make your alcohol group. Okay, and then of course you can then get rid, in your demercuration step, you want to get rid of that mercury acetate, which we can do with a reducing agent like sodium borohydride. All right, essentially the hydride ion from that can come in and knock out the mercury part and replace it with that hydride. Okay, so that's one reaction where we can get the Markovnikov addition without worrying about any carbocation rearrangements. If we want to make the anti-Markovnikov product, though, what we can do is what's called a hydroboration oxidation reaction. Okay, now in this reaction, in our first step, we're going to use a borane, okay, so boron trihydride, stabilized with THF, that's tetrahydrofuran. Okay, so we just have this in solution with the two, and the lone pair on the oxygen of your tetrahydrofuran donates into that empty p orbital on the boron and stabilizes it, essentially. Okay. In the second step, we add hydrogen peroxide and sodium hydroxide, and in this two-step process, we wind up essentially doing a hydration. We add water across this double bond, but notice that the alcohol group is added to our less substituted carbon. Okay, and therefore we've got our anti-Markovnikov product. So now the other thing to watch out for here is that we get a syn addition. All right, so in other words, our hydrogen and our alcohol group both add to the same side of that double bond. Okay, so in this case, where we've got a ring here in our cyclohexane, we're kind of locked into place here, we can see exactly how our hydrogen and alcohol group added on. Okay, so we get our two enantiomers, but you can see that In both cases, we have those two groups are cis to each other. We do not see the anti-addition products. We don't see those two groups trans to each other. So let's look at the mechanism to understand why. Quick note here about boranes. That boron with its sort of going under the octetual, which is a kind of a special property of boron, essentially causes it to behave like a carbocation. Okay, it doesn't have a positive formal charge like your carbocation, so it's not as strong. It's not as reactive as a carbocation. It's a little bit more stable. But again, similar concept here with this MTP orbital that's trigonal planar and can be attacked from either side. Okay. So yeah, so you'll sometimes see BH3 molecules sort of combining into dimers. They sort of clump together, and they share the electron density across their hydrogens. These are called 3-atom 2-electron bonds, also known as banana bonds. Okay, because of the sort of bent shape there. Okay, so that's why for hydroboration you want to use THF as your solvent. The lone pairs on your oxygen kind of donate into that MTP orbital, and they kind of stabilize that BH3 and prevent it dimerizing. All right, so if you have your BH3 molecules, how does it do a hydroboration? Well, it adds on like this to your alkene. So if you have an asymmetrical alkene, your boron goes to the less substituted carbon, and your hydrogen goes to the more substituted carbon. Okay. Now, as long as you have your BH3 floating around with, with excess alkene, you actually have this happen to each of the hydrogens on your boron. Okay, so you actually wind up getting a trialkyl borane. Okay, so your substrate, your alkene, adds on 3 times to your boron. Now, what does this transition state look like, right? What does this intermediate look like? So basically, you can see here that we kind of have this sort of partial positive charge forming on this carbon. Okay, so again, this is why the boron adds to our less substituted side. Okay, you could kind of make a sterics argument, but it's really more of a thermodynamic argument. This intermediate is a little bit more stable than if that boron added the other way. Okay, so that's why this partial positive charge is stabilized a little bit, and that's why the hydrogen winds up adding there. Okay, so that's once you've made your you've done your hydroboration step, we take this trialkyl borane, okay, and we're going to do an oxidation using hydrogen peroxide. Okay, so you take your hydrogen peroxide and you deprotonate it. Okay, so remember you're doing this in the presence of sodium hydroxide, which is a strong base. So it deprotonates your hydrogen peroxide, and you form hydroperoxide. Okay, now this hydroperoxide ion acts as a nucleophile, and remember you've got this electron poor boron, right? It's only got it's under the octet rule, so that attacks that boron and essentially transfers one of your alkyl groups to this oxygen. Okay, now in the process it kicks off your OH group from your hydroperoxide, and you form this alkoxide group instead. So essentially what you've done is you've taken this oxygen from your hydrogen peroxide and inserted it between the boron and that alkyl group. Okay, that's effectively what you've done. Now, you do this 3 times. Okay, so all of your alkyl groups undergo this process. Okay, and so you wind up. So so here's our alkoxy group, but we do this 2 more times, and we have 3 alkoxy groups on our borane. Now, if a hydroxide ion comes in, it acts as a nucleophile, okay, and adds onto our boron, making this intermediate. And we can see that we can kick off an alkoxy group as our leaving group here. Okay. And in doing so, you can do this 3 times. You'll eventually get all of your alkoxy groups kicked off. But for now, let's just follow one of these alkoxy groups. They pick up a proton, okay, from a proton source. You do a proton transfer, and that makes the corresponding alcohol. Okay, now again, why is this an anti-Markovnikov addition? Remember, your boron was initially attached to your less substituted carbon, right? Which means that the oxygen that gets inserted in between is attached to your less substituted carbon. And remember, that's what goes on to form this alcohol group. So that's why you're not following Markovnikov's rule. You make the anti-Markovnikov product. Okay, it's because of that hydroboration step that controls where that alcohol group's going to go. All right. So something again to keep in mind with your stereochemistry. Again, you have the possibility of forming chiral centers. Okay, so keep in mind that since your boron is trigonal planar, just like a carbocation, again, you're going to get a racemic mixture of products. Okay, so if you wind up making a product with a chiral center, because your boron can have add on that alkyl group to either side of it, or the boron adds onto either side of that alkane of that alkyl group, you can wind up with a racemic product. Okay, so yeah, so here's an example of so here we have this alkene, and you can see that if we look at these 2 carbons, our boron and therefore our alcohol group is going to add to our less substituted carbon over here. But note that we can have that OH group add to either side. It can either attack from from into the page here or sticking out of the page here. Okay, and notice that we still have that syn addition that we talked about. So the hydrogen we add on is on the same side as that alcohol group. Okay. All right, with that in mind, let's practice this. Okay, so take a second and draw the products of the hydroboration oxidation of these 2 alkenes. Okay, so if you recall when it comes to a hydroboration oxidation, we're going to do an anti-Markovnikov addition. So when we look at our alkene over here, out of these 2 carbons, this one's less substituted. So this is the one that's going to get our OH group. Now remember though, that OH group can add to either side of this carbon. Okay. Now the hydrogen, of course, is going to add to the same side as that OH group. So wherever your OH group is going to go, that methyl group is going to stick in the opposite direction. Okay, so our products are going to look like this. Okay, so here's our methyl group up here that's going to stay the same, but I could have my alcohol group sticking out here. Okay, and that means the hydrogen that's added on here will also be cis to this because of that syn addition. So if that hydrogen is sticking towards me, this methyl group over here is going to be sticking away from us. Likewise, we could have another molecule like this. Again, here's our methyl group, drawn very poorly. And let's say our alcohol group gets added on the opposite side, so sticking into the page. That hydrogen that gets added on would also be pointing away from us, which means this methyl group is going to start pointing towards us. So here are our 2 products. Now for this molecule over here, again, we're going to see the same thing in that our alcohol group is going to add to this less substituted carbon, okay, when we do our hydroboration oxidation. But the interesting thing here is how that syn addition is going to affect the rest of this molecule because it's a bicyclic compound. Okay, so what's going to happen here? Let's say for this 6-membered ring over here, right? Let's say we have our alcohol group add on here in this axial position, so it's adding up on top here, well, the hydrogen that we're adding on this side of that double bond is also going to be on top here, which means that in this case it's going to be, if it's going to be pointing upwards, that's going to make it equatorial, which is going to make this group over here axial and therefore point downwards. Okay, so it's going to kind of look like that. Okay. Conversely, we could have the rest of the molecule look, you know, the same. So I could have this add on here like that. But if this hydrogen is going to be, you know, axial pointing downwards, that means this OH group is going to be equatorial pointing downwards as well. Oops, so it should be down like that, OH. Okay, which means that this group is going to be axial upwards. This is going to be interesting to draw. Sort of like that, I guess, is what that's going to look like. This is probably not the best drawing, but it's essentially going to look something like that. Okay. Again, this is, you know, a tougher problem than you'd probably expect to see on a quiz or exam, but that's essentially what you want to think about. You want to think about how that syn addition is going to affect the you know, just the spatial arrangement, the stereochemistry of the rest of the molecule. Okay, so let's look at hydrogenation. Hydrogenation is the addition of hydrogen across a double bond. That's an H2 molecule, which makes things a little bit straightforward. You've got just a hydrogen atom added to each carbon. Unlike all the other examples we've looked at so far with hydrohalogenation and hydration, we're adding a symmetrical molecule across our double bond, which means that now regiochemistry isn't an issue. You don't have to worry about Markovnikov's rule here, because it doesn't matter which carbon gets the hydrogen. They both each get one hydrogen. Okay? Now, that being said, you still have to consider stereochemistry in, are we doing a syn addition or an anti-addition? Okay? Are both of our hydrogens going to get added to the same side of the double bond or on opposite sides of the double bond? Okay. Now, what we do observe in the case of hydrogen being added on with a platinum catalyst or some metal catalyst in general is that we see a syn addition. Okay, so we would wind up seeing this ethyl group and this methyl group, they would wind up being cis to each other. These two trans isomers we see here, these are not observed, okay? Because in order to make these, you'd have to have an anti-addition. All right. So adding a hydrogen molecule across an alkene is actually a highly energetic step, right? We definitely, you know, there's a large activation energy for that direct reaction. So instead, we need to use a catalyst to make this reaction happen. Okay, so we go through some alternative mechanism that involves forming some sort of complex with that metal, and that allows the reaction to happen much more normally under like, you know, much more reasonable conditions. Okay, typical metal catalysts that you see for these types of reactions include things like platinum, palladium, nickel. Those are typically the metals you see involved in these types of reactions. Okay. Now, if you want to see why this is a syn addition, this is kind of what happens. Essentially, your alkene absorbs to the surface of your metal. It gets, you know, sort of attracted to the surface of your metal. You have hydrogen molecules also adsorbed to the surface, but what happens with the hydrogen molecules is that the hydrogen-hydrogen bonds break, and instead you form hydride bonds with the metal. Okay, so you have metal hydride bonds that form. So you have these hydrogen atoms or hydride atoms, you know, just sort of added on to the surface of the metal. Okay, so essentially then the alkene kind of, you know, you have your hydrogen add to your carbon. Okay, so it's kind of you have this double bond open up and pick up one of the hydrogens, as you can see here. So you're just coordinated just by one carbon, you know, metal bond, and then of course a hydrogen comes in, you know, sort of adds on to, in a concerted process, adds on to that carbon while simultaneously breaking this carbon metal bond. Okay, and that gives you the resulting alkene. Okay, so if we were to add, hydrogen across this double bond, again, we want to do a syn addition, and so these two methyl groups would be cis to each other. So they'd either both be pointing towards us, with shown with solid wedges, or they'd be pointing away from us with dashed wedges, but they would still be cis to each other. Okay. Now, the quick thing you realize then is that these are the same molecule. This is a meso compound. There's a mirror plane going through the middle here. So in your product, there's also still that same mirror plane. So even though these are both chiral centers, they wind up kind of canceling each other out. Okay, so here's the two products you would expect to see, where those two methyl groups are cis to each other, but the funny thing is that they're the same molecule. You could rotate this molecule. You could imagine you've got an axis going here. If you rotate it 180 degrees along this axis, you would get this second molecule, so they're identical. Okay. Now, that being said, while you have a solid metal in solution with your alkene and hydrogen gas bubbling through, we call this a heterogeneous system. These are different phases, right? We're having this reaction occur on the solid surface of our metal, okay? With most of our reagents, so our catalyst is a solid, but our reagents are in a solution, okay, in a different phase, hence heterogeneous. That being said, it's possible, instead of having a solid catalyst, to have a catalyst that is also dissolved in the solution. We call this a homogeneous catalyst. Okay, so it's possible to get your metal center using some sort of metal complex that will dissolve in the solvent you're using. Okay, so an example of this would be Wilkinson's catalyst, for example. Wilkinson's catalyst here is a rhodium atom here with three triphenylphosphine groups plus a chlorine. Okay, and this will also do a syn addition to your alkene. It'll add hydrogen in a syn fashion here. The advantage here is you've got a homogeneous system instead of a heterogeneous one, which has its own set of advantages, such as you tend to have better selectivity for one set of products versus another, both just regioselectivity and enteroselectivity. We'll get into that in a little bit, yeah, sometimes you just see higher yields and things like that. I mean, heterogeneous catalysts have their own sets of advantages too, of course. It's easier usually to separate out a heterogeneous catalyst. They tend to be more durable, so you get just more turnovers out of them, just more. They just last longer. You can recycle them a little bit more, things like that. But that being said, from the type, from a product standpoint, a homogeneous catalysis tends to, to have significant advantages there. Okay, now I mentioned that you could have greater enantioselectivity. What do I mean by this? Well, it is possible to do asymmetric hydrogenation, not because hydrogen's asymmetric, but because your substrate's asymmetric. So you can add your hydrogen selectively to one side of your alkene versus another. Now, to do this, you need, instead of using a symmetrical phosphine here, you could use an asymmetrical one. You could use something that's chiral. We have three different groups here. Okay, and of course that phosphine is going to be attached to our metal center, so that's a fourth group. And that makes this phosphorus a chiral center. And depending on the bulkiness of these groups that we're using here, that will definitely force you to make one product versus another. Okay, so Knowles here, a modified Wilkinson's catalyst. I believe Knowles was one of the scientists who won the chemistry Nobel Prize, along with Nuyori and Sharpless, I think, for work with this sort of asymmetric catalysis. So essentially, the bulkiness of these groups and the very selective bulkiness, bulkiness in one direction, kind of causes one of your products to have a much lower activation energy than the other. Okay, and that's why they're enantioselective. They prefer, you can see that one of your enantiomers is a kinetically favored product compared to the other one. Okay, and so that's why we have some enantioselectivity here. Okay, so here we've got the ruthenium binap catalyst. This was actually Noyori's catalyst. The other guy, one of the other, three people who won that Nobel Prize. You have these two phosphine groups that both add on to this ruthenium. And you can't see it here, but basically the hydrogen that's sticking off this carbon and the hydrogen that's sticking off this carbon can't overlap, right? They kind of they're essentially um, they are kind of occupying the same space, so it causes this molecule to sort of corkscrew a little bit, and that's again what makes this gives this molecule its sort of 3D sort of chirality. Okay. I think actually I could probably show you a picture from a presentation I gave in grad school about this. Hold on one second, let me pull that up. All right, so this is a really old PowerPoint that I gave back in like my second year of grad school. So I think this was probably like 2005. But anyway, I think I talked briefly about Noyori's catalyst here. So I like the visual from here because this really shows where that chirality comes in. Okay, so you can see that those hydrogens I mentioned again kind of sterically clash with each other, and that's what kind of causes this sort of corkscrewing of this molecule. So it's a bidentate ligand. It kind of attaches to a metal, it bites onto it from two phosphoruses, two phosphorus atoms. But since these two naphthalene groups are kind of attached to each other, and again, that steric hindrance from those two hydrogens causes them to sort of skew a little bit like that. Okay. If you want to see a visual, by the way, of why this catalyst sort of encourages an asymmetric hydrogenation, you can see here. This is now this is not an alkene. This is a ketone, but it's going to be a similar concept here. If we have this asymmetrical ketone here, or anything with a double bond, here we've got a bulky phenyl group, which is a benzene ring, and a smaller methyl group, right? The molecule has to add on like this. If we flip the molecule over so that the hydrogens add on to the opposite side, you can see that these two phenyl groups kind of clash with each other. These two bulky benzene rings sterically clash, and therefore this does not add on this way, right? The activation energy for this step, for this type of product, it's too high in energy. By the way, you don't have it add on the other way, and having it add on that side by rotating the molecule, 120 degrees that way. That also is forbidden from this phenyl group on this side as well. Okay, so that's again what causes the enantioselectivity when you have a catalyst like this. All right, so again, like with this example here, with this sort of asymmetric alkene, and using this chiral catalyst, you can see that we add hydrogen in such a way that this methyl group has to point this way as opposed to sticking into the paper, into our screen, and that's really enantioselective. We get 95% of our product is that product. So, all right, so yeah, so that's remember when we add hydrogen, when we do a hydrogenation using a metal catalyst, these are regular heterogeneous catalysts, by the way. So we're just going to do a regular syn addition here. So keep that in mind for how these groups add on. Okay, so in both cases we have an asymmetric substrate. So think about how that's going to affect the product we make. Okay, so when we add our hydrogens to this, so we can either have, so if we have our hydrogens add on top of this double bond that's over here, this methyl group gets pushed away from us. Or if we have them add to the bottom of that bond, then that methyl group gets pushed towards us. Okay, so these are the two possible products we'd see. With this molecule, of course, we can have our hydrogens add on top here, which would, of course, push this. This double bond disappears, and this pushes this group downwards. So, it kind of looks like, again, if we have our hydrogens adding up here, that's going to force this equatorial group to be axial. Okay, so it's going to look like that. Or, of course, if our hydrogens add onto the bottom, that's going to push this carbon bridge upwards. So it kind of looks like this. Okay, so if we, oops, that's one bond. So instead of, so if our hydrogens add onto the bottom here, this gets pushed upwards like that. Okay. All right, so those are our two possible products. Yeah, actually, I think looking at this, I'm trying to see if these two are oh yeah, that's still a chiral carbon, right? And is this a meso compound, I guess, is the good question. Oh, there's your problem. This is a meso compound. There's a mirror plane going through the middle of this molecule. So I just realized these two molecules are the same molecule, just flipped over. Okay, so actually, yeah, that's an interesting thing to consider here. These are both the same molecule. There's a mirror plane that's cutting right through the middle. Okay, so the next step is halogenation. What happens when you try to add a halogen across your double bond? Okay, so like hydrogen, so just like your hydrogenation, your halogen has two identical atoms in its molecule, right? You just have two halogens instead of two hydrogen atoms. Okay, now you've actually already seen this a little bit in lab. Or if I get this PowerPoint out early enough, maybe you haven't seen this in lab yet. But we're going to do a lab where we add bromine across the double bond of tranexamic acid, and you're going to see from that. From your product, you're going to figure out how the bromine added on, whether it was a syn or anti-addition. If we haven't done the lab yet, this is going to give you a bit of a spoiler alert in terms of what the answer is to the lab. But anyway, we'll get into that in a second. So again, basically, we're just adding our halogen atoms across our double bond. Okay, so typically, so when you have an alkene and we react with a halogen, each of those carbons of our double bond get one halogen atom. Okay, so this is a very useful reaction because hydrocarbons generally don't have a lot of synthetic utility, but this is an easy way to add halogens to them and then turn them into very useful molecules with a very useful functional group, right? We've got alkyl halides now, which we've seen we can do substitution reactions, we can do elimination reactions. There's all sorts of cool things we can do with that. Okay, so like I said, spoiler alert here, but we are going to do we're going to have our halogens add on with an anti-addition. Now, typically when we look at halogenation, we're typically looking at the addition of chlorine or bromine. With iodine, iodine is just it's just too slow a reaction to make it practical. With fluorine, fluorine is a little too quick. It reacts very violently. Again, that just makes it not very practical. So most of the halogenation reactions you're going to see are going to involve chlorine and bromine. All right, so something to keep in mind there. But as I said, this is going to be an anti-addition. We're going to see that our bromines are going to be, if they are locked into place like this, like with our cyclic compound here, we see that these two groups are going to be trans to each other. Okay, and of course there's two options for that. So something to keep in mind. Okay, so how does halogenation work? Right? Well, our halogens are nonpolar molecules, right? We've got two atoms that have equal electronegativity, right? However, when we're looking at these large halogens, especially bromine, they're very squishy, to use a non-technical term, right? They're very polarizable. Because they have so much electron density around them, it's possible to push that electron density temporarily to one side, and therefore get a partially negative and a partially positive side to your molecule. Well, when you make a part of your molecule partially positive, well, it's now very electrophilic. A nucleophile can easily attack that. And in this case, our nucleophile is going to be our alkene. Okay. The nice thing about that resulting partially negative side is now you've set it up to be a great leaving group. Okay, this bromine is going to leave as a bromide ion, which of course is a good nucleophile in its own right, which will in turn be ready to react with the corresponding carbocation we form. Okay, so here's what happens, right? Our alkene attacks, does a nucleophilic attack on our bromine molecule, kicks off that bromide leaving group. And now, of course, our bromide can be a nucleophile. And here we've got a carbocation. And we've seen that carbocation intermediates cause, they're flat, right? They're trigonal planar. And typically a nucleophile can attack either side. So why do we see only the anti-addition product? Why don't we see the syn product? Okay, that's because we want to take a little better look at what this carbocation intermediate actually looks like. Okay, what does that bromine group that's already on here do to that carbocation? And it's actually something we've seen before. All right, we actually form a bromonium ion, right? And I say we've seen this before, not with bromine, but with a mercury and a boron. Okay, we've actually kind of seen this sort of bridged intermediate where this bromine is essentially blocking off one side of our carbocation. Our bromide nucleophile has to attack from the opposite side. Okay, it has to attack from the opposite side as that bromine, and therefore that's why we get the anti-addition product. Okay, so there we go. That's our anti-product. Yep. So that's how we get an anti-product. Now, keep in mind, by the way, that just because when you open up your double bond, you can rotate around that carbon-carbon bond freely, right? So be aware of that when you're trying to design certain products. So, for example, here with our cis-2-butene, if we do our anti-addition of bromine, we're going to get these two products. But let's say we wanted to make, we wanted to add bromine. We wanted to have a molecule with bromine, the two bromines cis to each other. Did this, violate that anti-addition that we see? And the answer is no. If you use the trans-alkene, if you use trans-2-butene instead of cis-2-butene, you'll wind up getting this product, okay? You'd have to rotate this carbon-carbon bond to get it into this conformation, but it is the same molecule. Okay, so with that in mind, let's try drawing the products for these. Again, remember your bromine, or chlorine in the case of the second one here, those add, we're going to do an anti-addition. So your two halogens are going to be trans to each other. So keep that in mind when you draw these two products. Okay, so you should have, if we're drawing this molecule here, okay, and we have this methyl group sticking towards us. Let's say we add, this bromine over here is facing towards us. That means that this bromine over here is going to be away from us, because remember, it's an anti-addition, so they're going to be trans to each other, which means that this methyl group is going to be pointing towards us. Okay, and of course, we could have another molecule where, again, this methyl group's, oops, I really need to get better at drawing these methyl groups on my graphics tablet here. Okay, so that methyl group's pointing towards us. Okay, so let's say now this bromine is going to be pointing away from us, which means that this bromine's pointing towards us. And of course, that makes this methyl group point away from us. Okay, so there's our two products. Okay, and of course, similarly here, we've got to think about having our chlorines add to opposite sides. So actually, that makes this a little bit easier to draw for at least this original molecule. You can have this chlorine sticking up axially here and axially down here. They'd be trans to each other that way. Okay, so it would look like that. Okay, let's draw that. There we go. So that chlorine sticking up here, axial. That chlorine is going to be sticking down here, axial. Okay, and of course we could have them go the other way, and that would kick this group here and this group here. This bridge would be kicked upwards. This bridge would be pointing downwards, and our chlorines would be in equatorial positions. Okay, now we just saw a halogenation reaction where we take our halogens, react them in solvent like carbon tetrachloride, which is not going to interfere with our it's a non-polar solvent that's not really going to interfere too much with our carbocation, or bromonium ion rather. But instead, we can use a different solvent like water, and we can do what's called the halohydrin reaction. Now, the hydrogen part here is where that water molecule is our nucleophile in that second step of the reaction. Okay, so by changing our solvent, we now make a product. Instead of getting the dihalide product, we wind up getting a product that has a halogen and an alcohol group. All right, that's our halohydrin reaction. Okay, so now the reason that we get a lot of this product is if we're using water as our solvent, we have a lot of that nucleophile available to attack that, not carbocation, that bromonium ion. Okay, so notice here that, we're still doing an anti-addition, right? Because that bromine still blocks off, if I go back to the previous slide, the bromonium ion has that bromine blocking off one side. So your water molecule has to act on the opposite side of your bromine and make that anti-product, okay, as you can see here. And of course, it could attack either carbon and make the corresponding enantiomer. Okay. So notice that here we have, we could use chlorine and water instead of bromine and water and do the same thing. Okay, except now we have a chlorine instead of a bromine. Okay. Please note, in these reactions, we use water as our solvent. It's possible to use an alcohol as your solvent, by the way. And then instead of getting an alcohol group over here, you would get an alkoxy group. Okay, so if you're curious about how that works, basically, instead of HOH, we have an R group over here. Okay, so instead of water adding on here, we have an R group of some side, and that plucks. This loses that proton, right? So another molecule here, or another alcohol here, plucks off that proton, and then so instead of hydrogen here, we have this alkyl group. Well, this is an alkoxy group. Okay, so keep that in mind if you ever use an alcohol instead of water for this reaction. Okay, in the case of the halohydrin reaction now, we have to watch out for regioselectivity, because while our bromine or chlorine, our halogens, are symmetrical, water is not, right? It's not the same as your halogen, and so your halohydrogen reaction is asymmetrical. And so you've got to think a little bit about the regioselectivity involved here, all right? What we're going to notice is that alcohol group coming in is going to add on to the more substituted carbon. So it's kind of like a little bit like that Markovnikov selectivity that we saw earlier. Okay, now why is that? Well, there's going to be you've got to think a little bit about what that transition state looks like, and there's going to be an electronic argument here to be made. Okay, so if we look at our bromonium ion, all right, and we look at the transition state of that bond breaking, we see that the partial positive charge is going to be a little bit more stable on the side that has that's more substituted, that has more alkyl groups attached to it. And therefore, that side is going to be more attractive to your nucleophile coming in. Okay, or rather, not so much that it's going to be more attractive, but the energy of this transition state is going to be a little bit lower, and therefore there's going to have lower activation energy. Okay. Yeah. Oh, by the way, if you're worried about sterics, okay, if you're trying to make a sterics argument for why this wouldn't happen, please note that water is a very small molecule. So from a steric hindrance standpoint, these alkyl groups don't really bother it too much. Okay. So with that in mind, go ahead and try drawing out the products of this. Okay. So you want to keep in mind, of course, our stereoselectivity as well as our regioselectivity. Okay, so remember now, out of these two carbons, which one's going to get the bromine and which one's going to get the alcohol group from our water? Well, remember, the alcohol group winds up on the more substituted carbon. That's this carbon down here. Okay, so we know that our bromine is going to wind up on this carbon up here. So again, though, we've got to consider, stereoselectivity. If this bromine is going to be pointing towards us, that means the alcohol group that adds on here is going to be pointing on away from us, which means this methyl group is going to be pointing towards us. And of course, we can get the corresponding diastereomer. So again, that methyl group is pointing towards us. If that bromine adds on the side away from us, that means this alcohol group is going to be pointing towards us. And of course, that methyl group then is going to be pointing away from us. Okay? For this molecule, which side gets the chlorine, which side gets the alcohol group? Well, the alcohol group is going to attach to this carbon over here, and the chlorine is going to attach over here. Okay, so, and if you want to, see what that looks like, again, because of the anti-addition, in the more straightforward answer, the chlorine is going to be here, and our, oops, I drew that in a really weird way, but this alcohol group is going to be pointing downwards here. I'm just going to extend that bond to make it a little bit easier to see. Okay, and of course we could draw it, we could have our chlorine be axial here, or equatorial here, and our alcohol group also would be equatorial, and it would force these groups to be axial. Okay, now we could also add two alcohol groups across our double bond. We call this dihydroxylation. So our hydroxyl group is another name for an alcohol group, and so dihydroxylation tells us that we're adding two alcohol groups. We're making a diol. Okay, so that's an alcohol, but there are two alcohol groups, hence diol. Now, this can be done in either an anti-dihydroxylation, where our two alcohol groups are trans to each other, or we can do this with a syn dihydroxylation, where they are cis to each other. Okay, now you're going to need different reagents and different conditions accordingly to do this. So how do we do an anti-dihydroxylation? Well, one way to do it is to form an epoxide by using a peroxy acid over here. Okay, so a peroxy acid is just a carboxylic acid with an extra oxygen present, okay, between your basically it's between the acidic hydrogen and the oxygen of your carboxylate group. You just have an extra oxygen there, so it's like a peroxide in that group. All right, so essentially it looks like this. So if I were to draw this as a peroxy acid, so if this were a regular carboxylic acid, this is what we would see, right? For a carboxylic acid, a peroxy acid has an extra oxygen in here. So basically you have that. Okay, so your peroxy acid basically adds an extra, basically adds an oxygen across your double bond, making an epoxide. Okay, and then you can have a water molecule come in as a nucleophile and attack that carbon and form the corresponding diol. Now, just like with our bromonium ion and all those other examples, that oxygen's blocking off one side of that alkene, or what used to be that alkene. So your nucleophile coming in has to attack the opposite side, and that's why we have an anti-addition there. Okay, so here's our peroxy acid. You can see what the transition state looks like for forming that epoxide. Okay. And then, of course, keep in mind, epoxides are pretty reactive. There's a lot of ring strain in that sort of triangle, that little sort of triangular half of the molecule. That's going to be like, it's trying to be a 60-degree angle, which obviously we know that that bond angle, that sp3 carbon wants to have 109 degrees. So it's very significant. Okay, so water, as we've seen, isn't a great nucleophile, so it sometimes helps to do this in the presence of an acid that protonates your oxygen, okay, and makes this a little bit more reactive. So your nucleophile attacks either carbon and produces your corresponding diol once you deprotonate that water molecule. Okay. And so again, notice the similarities between our epoxide, our bromonium ion, our mercurinium ion, and notice that's why we tend to have that sort of anti-addition that we see. Okay, I mentioned that you can do a syn hydroxylation. Well, in order to do that, we need to use a metal center, and typically we're going to use osmium 8 oxide. Okay. So here, our osmium essentially adds on both oxygens in a concerted step. It kind of forms this complex over here, this cyclic osmate ester, and then you can then reduce that down using sodium sulfite or sodium hydrogen sulfite, and that clips off your osmium and converts these into alcohol groups. But again, notice that because these were both attached to the same metal center, that's why we have the syn addition product. Okay, now in the case of osmium 8 oxide, this not only is osmium very expensive, but this is also very toxic. So you generally don't want to use this in stoichiometric amounts. Instead, you want to use catalytic amounts of osmium 8 oxide and get it regenerated again. So you add in something else stoichiometrically that regenerates your catalyst back again. So for example, some sort of peroxide would work here, okay, or some source of oxygen. Okay. Fun fact: this was essentially the back when I was in grad school, my research group essentially did this sort of stuff. We each did different. We used different metal centers. I personally used ruthenium and palladium more, but the goal was to make catalysts that did alcohol oxidation reactions, essentially, and turn over our catalyst using something like hydrogen peroxide or even oxygen gas. But anyway, if you're bored someday and you want to talk about research and stuff, I'm sure I could talk to you about that stuff. Okay. So in addition to osmium 8 oxide, it's possible also to use permanganate. So you could use, for example, potassium permanganate, and it'll get the reaction done, but it's also more reactive than osmium 8 oxide. And therefore, you've got to do this under really mild conditions. You need to cool this down to avoid the reaction, just getting either explosive or just making a whole bunch of byproducts you don't want. Okay. Another reaction we can do with alkenes is to do what's called oxidative cleavage or ozonolysis. So basically, if you use ozone, you can split your double bond into two carbonyl compounds. Okay, so effectively, if you want to picture what's going on, just sort of cleave this in half and put an oxygen on each side of that. Okay, so the reaction conditions for this are you add ozone and you kind of quench the reaction with dimethyl sulfide. Okay, so you also, in addition to dimethyl sulfide, zinc and water is another reducing agent you could use here. But basically, you have your alkene sort of add on, form this sort of ozonide molecule, this ozonide intermediate, through this concerted action here. And then again, in another concerted step, you have all of these, these electrons swing around and break this carbon-carbon bond, and also form carbonyl bonds instead. So notice that we formed a carbonyl here and formed a carbonyl here. Okay. Again, we have another cyclic pushing around of arrows, and we get another ozonide. Okay. And again, we can have these electrons move around, kind of similar to what we did here, but basically that reducing agent breaks this and removes an oxygen and leaves us behind with just these two, these two carbonyl compounds. Okay. So with that in mind, go ahead and have a look at these two molecules and ask yourself, what will the ozonolysis products look like? Okay, so again, remember you've got your alkene. You want to cleave your double bond here, and this double bond will be to an oxygen, and this double bond will be to another oxygen. Okay. Likewise, for this molecule here, notice that we've got three carbonyls. Remember, four carbonyls. Remember, two of these carbons were probably attached to each other in some fashion. Okay. This carbonyl and this carbonyl were probably not connected. That would be too tight a ring to connect together. So if I were to guess, I would say probably connect this carbon to this carbon and this carbon to this carbon. Okay. If you're having trouble doing this problem, my advice is to try numbering carbons, and then that tells you how many carbons are going to be in your ring that you're going to form from these. Okay, so if you want to see the products of these reactions, so for that first one, like I said, you're cleaving over here essentially. So you're going to form a carbonyl this way and a carbonyl this way. Right, so if this is of course kind of messy and hard to look at, so it sometimes helps, like I said, to draw, to count carbons. We've got 1, 2, 3, 4, 5, 6 carbons. So you could just draw, a 1, 2, 3, 4, 5, 6 carbons there, and draw your carbonyls accordingly. So for example, I have, this carbon over here has my carbonyl, and this second carbon on this side has a carbonyl. So I know I have a carbonyl here, and here I've got my second carbon this way. This is the one that has my methyl group. Okay, so I want to keep the same configuration here. Okay, so accordingly, if this is R or S, we want to draw that the same way. Okay, so looks like if that hydrogen's pointing away from us, goes 1, 2, 3. It's going to go counterclockwise, so that's going to be an S enantiomer. So if I have my methyl group here, pointing towards us, the hydrogen's away from us, that would also be counterclockwise if that's pointing towards us. So yeah, this would also be S. Okay, so that methyl group is pointing towards us. Okay, so that's the nicer, neater way of drawing that molecule. But basically, this carbon and this carbon were attached to each other. All right, for this molecule here, we would have probably had these two carbons connected to each other, so we can try and figure out how big this ring would have been. 1, 2, 3, 4, 5, 6 carbons. Okay, and likewise, this carbon was probably connected to this carbon here, so that would give us 1, 2, 3, 4, 5 carbons. We have a 5-carbon ring that way. So basically, we should, it might be easier here to probably number the carbons to see exactly which carbons are connected to which. So for example, if I number these 1, 2, 3, 4, 5, 6, okay, and then we can see that carbons 3 and 4 are part of this other ring. Okay, so I could, well, let's first try drawing that 6-membered ring. 1, 2, 3, 4, 5, 6. Okay, so let's have carbons 3 and 4 over here be these two carbons over here. Okay, so we want a 5-membered ring there. 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. All right, there we go. So there's our 6-membered and 5-membered rings. So if this is carbon 3, okay, and 2 and 1, we have a double bond between carbons 1 and 6. Okay, so 1, 2, 3, 4, 5, 6. Okay, so that's what's connecting these two carbons here. Okay, and for carbons 3 and 4, we have a double bond between carbon 3 and this other part of the ring. Okay, so if this is carbon, so we have, let's see, 1, 2, 3, and so we have a double bond with this carbon and the closing of the ring here, so that's this double bond there. All right, so that's what your original diene would have looked like. Okay, so again, like at the start of this chapter, at the start of this video, we kind of looked at, we kind of summarized all of our addition reactions and saw that essentially what we're doing is we're taking a molecule, we're splitting it in half, and we're adding each half to one of the two carbons of our double bond. Okay, so essentially that's what you need to do when you're looking at your reactants. Like you want to say, all right, what are the two things I'm adding to my two carbons? Then you want to take into consideration how those two things add. Does regioselectivity come into play here? If you have an asymmetrical alkene and an asymmetrical a molecule that you're adding, you want to think about, okay, which carbon gets which of these halves? Okay, that's what we call the regioselectivity, and you're basically looking at Markovnikov's rule and determining, oh, do I get the Markovnikov addition product here, or is the type of reaction I'm doing prone to give me the anti-Markovnikov addition? Okay, so that's something you have to keep in mind. In addition to regioselectivity, you want to consider stereospecificity. Okay, so are we doing a syn addition or an anti-addition? Are the two halves of these molecules going to be on the same side of that double bond or on opposite sides of that double bond? Okay, so you want to keep that in mind, especially when you're drawing out, the sort of 3D structure of your molecule, the solid or dashed wedges. Think about where your groups are going to be in three-dimensional space, right? And of course, remember, if you have trouble seeing that, you're always welcome to use a model kit for a quiz or exam, and so feel free to use that to help you draw things out. Okay, now while memorizing each of these steps is great, it's a good shortcut. Keep in mind, especially for these the reactions that go through a carbocation intermediate, and you have some potential for rearrangements. Please be aware that knowing the full mechanism will probably serve you better. Okay. So let's try a practice problem out here. So feel free to pause this and try this out. But let's analyze this now. So we have our alkene here, right? We're going to add across this double bond. Our reagent here is osmium 8 oxide, right? We're using it in catalytic amounts, and there is, the molecule NMO, which remember is an oxygen source, which essentially helps turn over the catalyst, right? We're just going to replenish it with more oxygen. So when you look at this reagent, you should be asking yourself, what does this do, right? What type of addition reaction is this going to carry out on my alkene? And if you recall, your osmium 8 oxide here is going to do a syn dihydroxylation. Okay, so both of your your metal centers are going to coordinate 2 oxygen bonds to that alkene, and it will wind up essentially adding 2 alcohol groups. But it's going to be a syn addition, so they're going to be on the same side of that double bond. All right, so if we're looking at our product for this, it's going to be, so here's our 5-membered ring. We know that we've got our methyl group sticking up here. We could add both of our alcohol groups to the same side, from the top, let's say here. So let's say these are both sticking up. Okay, so here's our 2 OH groups. Okay, then what happens to this methyl group? Well, if this OH group sticking up, then this methyl group's pointing downwards, right? Now, of course, we could also have added those OH groups to the bottom of the molecule from the bottom. Okay, so that's sticking downwards, and that's sticking downwards, which of course then means that our methyl group's pointing upwards. Okay, so that's kind of how we would approach a problem like that. So far now in these last 3 chapters, we've found 3 different types of reactions, and we've essentially added them to our kind of synthetic toolkit, right? We can see ways to change functional groups through these 3 reactions. We can, in this chapter we've learned addition reactions where we add molecules across a double bond. 2 chapters ago, we looked at substitution reactions where we can swap out, one group for another. And then, of course, we've seen in the last chapter, we saw elimination reactions where we can eliminate a leaving group and a beta hydrogen to form an alkene. So kind of basically the reverse of our addition reactions. Okay. So keep that in mind, that these are all tools we can use to make molecules that we want. So this gets asked in 2 ways. You have a starting molecule, and if you are given the product you're trying to make, you can think about what reagents you need to make that happen. If you're given the starting molecule and the reagents that you would react it with, you can then predict what product you would make. All right, so those are the 2 ways essentially you get asked a synthetic problem, and keeping in mind what types of reagents do what is going to be a very useful tool here. All right, so looking at this as our starting molecule, ask yourself what reagents would give us this product. Okay, and then here's a second problem. What reagent would give us this product? Okay, so feel free to pause this video, and if you get stuck, go back through the PowerPoint and see, what reagents would come in handy here. You'll notice that we're starting off with an alkene, and this product here has 2 different groups added onto those 2 carbons where that double bond used to be. Okay, same thing here. We've got 2 different groups. You can't see it, but there is an extra hydrogen now on this carbon. Okay, it went from being an sp2 carbon to an sp3, so that extra bond is to a hydrogen that's not shown. So think about what types of reactions we're doing here. Okay, so you've probably figured it out. Here we have a bromine and an alcohol group, right? So that should bring you back to your hydrohalin reaction. Okay, so think about what reagents will produce that. Well, remember, you've got to use bromine, bromine molecule, but you want to use water as your solvent. That's how you get that alcohol group added on. Okay. For this one, we're essentially doing a hydration reaction, right? That hydrogen plus our OH group, it's essentially adding water across this. Okay. Now, we've seen multiple reactions that do hydrations, so we want to take this a step further. Let's look at the regioselectivity of this and ask ourselves, is this following Markovnikov's rule? Is this not following Markovnikov's rule? And if it's following Markovnikov's rule, we need to distinguish further between using sulfuric acid versus doing a mercuration demercuration, right? Would going through a carbocation intermediate lead to this product or to something else? So these are things you want to consider. So first of all, is this a Markovnikov or anti-Markovnikov addition? Well, out of these two carbons of our double bond, okay, so if we look at our double bond initially, this one's going to wind up forming a secondary carbocation, okay, or sorry, I should, let's take a step back. This is a secondary, side. You've got only two carbons coming off of it, whereas this one's tertiary, right? So the fact remains that this is more substituted, and we have our alcohol group on our more substituted group, or our more substituted carbon, and therefore this is a Markovnikov addition. Okay, so that automatically rules out hydroboration oxidation, right? Because that would have given us the anti-Markovnikov product, so that can't be what happened, right? So we've got our two options here now of either using sulfuric acid, dilute sulfuric acid, to carry out this reaction, or we could have done a mercuration demercuration. Now, both of those would work, of course. In terms of your alcohol group here adding to a tertiary site, that's going to be the most stable carbocation you could form. There's no possibility of rearranging to something else, so sulfuric acid is a perfectly legitimate way to do this. That being said, you could also do a mercuration demercuration. That would also be correct. So that's another thing you want to watch out for in these synthetic problems. You want to consider that oftentimes there's more than one right answer, and so you need to be ready to see an answer that you weren't expecting. All right, you want to acknowledge that since you've got a multiple choice quiz or exam in front of you, the option they give you might not be the one that automatically pops into your head when you think, oh, how would I do this reaction? Okay, so something to keep in mind there. Now, with a one-step synthesis we just saw, things are pretty straightforward because everything happens in one step. You need to remember only one set of reagents. When it comes to multi-step syntheses, that's where things get a little bit interesting because you've got to have a little bit of creativity here. You've got to kind of think a few moves ahead, kind of like in chess, right? And so this is an acquired skill, and we're going to walk through this, not through just this chapter, but through multiple chapters. We're going to get better and better at this, okay? So don't panic if this doesn't come to you immediately. Just like when we were learning about three-dimensional molecules and thinking three-dimensionally, these are new skills you're picking up, okay? So don't panic if you're not immediately great at it, okay? But you start getting an eye for how these molecules are changing. You start noticing different way these molecules can change, and it'll definitely take some trial and error as you're starting to build that skill. Okay, so for example, if we see here, we've got a molecule where we've taken one functional group and we've essentially moved it. Now, this sort of rearrangement doesn't really have a single step that can do this. We haven't learned a reaction that does this. So what's actually happening is two different reactions. Okay, so we're taking our starting molecule, we're doing an elimination, right, forming an alkene, and then we're adding HBr across that double bond. Okay, but we're adding it in such a way that the bromine winds up here on this carbon instead of this carbon. If we added it to this carbon, we'd just be doing the reverse of this reaction. Okay, so keep that in mind. You want to take into account regiochemistry here, and sometimes stereochemistry or stereospecificity as well. Okay, so something to keep in mind there. Okay. So how does this work, right? Well, if we look at where the bromines wind up moving from and to, the two carbons involved are here, right? It's these two carbons. So that kind of tells us that that's where our double bond must be between those two carbons. So you should ask yourself, all right, for this elimination reaction to make that alkene, am I making the Hoffman product or the Zaitsev product? Okay, so again, you can, if it helps, try drawing both of them out. So remember, here's our bromine leaving group. You can remove your beta hydrogen either from this carbon or this carbon. Okay, there's two beta carbons you can choose from. The one on the right here forms the more substituted double bond. That's your Zaitsev product. And the one on the left, of course, is your Hoffman product. Okay, it only has one alkyl group coming off of it. It's mono-substituted. Whereas your Zaitsev product is tri-substituted. Okay, so think back to the last chapter where we looked at elimination reactions. How did we control the Zaitsev versus Hoffman product? Well, we use a bulky base to get the Hoffman product, right? So we know then that we want a smaller base, like sodium methoxide, one of those, to make our Zaitsev product, because that's what we need for this reaction. Okay, then of course we're adding HBr across that double bond. Is this a Markovnikov or anti-Markovnikov addition? That's something you want to consider, right? So when we add HBr across there, is that Markovnikov or anti-Markovnikov? The bromine's going to the more substituted carbon, so it's a Markovnikov addition. So we simply just add hydrobromic acid, and that'll be sufficient to get the product we want. Okay, so if we had to do it the other way around, you'd want to consider, well, what other reagents would we use? All right, so let's try another one here. So here we've got this alcohol group that we're moving to this carbon over here. Okay, now we've already learned a new technique now on how to do this, how to move a functional group. Doing an elimination reaction and an addition reaction will cause a functional group essentially to move. Okay, and we get to, by choosing regiochemistry rules, such as Zaitsev versus Hoffman, in the case of an elimination reaction, or Markovnikov versus anti-Markovnikov for a addition reaction, we can control where this group moves to. Okay, so that's something to keep in that synthetic toolkit or synthetic arsenal that you have. Okay, so this is essentially what we're doing, right? We've got our alcohol group here, and we're moving it to here. So it's these two carbons that are probably where our double bond is going to be in our alkene intermediate. And so that's what we see here. Here's the product of our elimination reaction. And then we do an addition reaction where we add an OH group over here. Okay, so again, think regiochemistry. Is this the Zaitsev or Hoffman product for our elimination reaction? Well, here's our OH leaving group. Okay, and so we've got two different types of options for our beta carbons. This beta carbon and this beta carbon are identical, right? So if we formed a double bond here, that would have been our Zaitsev product, right? We would have had a tri-substituted double bond. Whereas here, if we remove from this beta carbon, this double bond is only di-substituted. That's our Hoffman product. Okay, so think about what kind of base you'd use for your Hoffman elimination. Okay, so you can't simply just use, just use an acid to protonate this water, have it leave. Because then you would get a, you would get the Zaitsev product, of course. All right. So you want to use a bulky base to produce this, right? But of course, the problem with an alcohol group, so it's when you start thinking through this problem, you start noticing more problems, and you've got to address them. So we want to do a Hoffman elimination, so we need the bulky base, tert butoxide. Okay, so you could use, let's say, potassium tert butoxide as your base. But that alcohol group is not a great leaving group. You want to protonate that, right? And so we can't really protonate it if we're using a bulky base to eliminate it. So we want to probably swap this out for a better leaving group. For example, maybe a tosylate group. Okay, that might make things a little bit easier. Okay, so you can see that we first converted to a tosyl chloride, to a tosylate group using tosyl chloride and pyridine. Okay, we get a byproduct of pyridinium chloride, which just like crashes out of solution, and kind of drives this reaction forward. But essentially, this is how we would swap out our OH group for a tosylate group, which is a great leaving group. Okay, again, this might be another reaction you want to kind of add into your toolkit. Okay, and of course, then once you get to this point, then doing your elimination is really straightforward. You take your bulky base. Here's your great leaving group. The bulky base ensures that this is the beta carbon uprotonate or deprotonate, and there's your double bond. Okay, now let's look at that second reaction. We're adding an alcohol group to this carbon, and it's not shown, but we're adding a hydrogen to this carbon. So we're doing a hydration reaction. Is this a Markovnikov or anti-Markovnikov addition? Well, our OH group is going to the less substituted of the two carbons, so that's an anti-Markovnikov addition. Okay, so think about what you would use to do an anti-Markovnikov hydration reaction. Okay, so if you go back to hydration, you'll see that the only way to do this that we've learned is a hydroboration oxidation. Okay, so we use our borane in THF, and subsequently in our second step we use hydrogen peroxide and sodium hydroxide, and that will do the reaction and produce this product that we're looking for. Okay, so now is stereochemistry an issue? Like so far we've been ignoring that. In this case, it really isn't, right? We've got neither of these carbons are chiral, so we don't have to consider, which side does our group add on. Do we have to do a syn or anti addition to get the stereochemistry we want? Okay, so that's really not an issue. Okay, it's like this carbon up here has two ethyl groups coming off of it. This carbon down here has two hydrogens on it, so neither of those is going to be chiral. Okay, so now here's another look for us. Here we have a double bond moving. Okay, instead of having another functional group, a particular substituent moving, now we have the double bond moving. We can take a similar approach though. Instead of doing an elimination to make an alkene and then an addition to having your functional group added on, now we can start off with an addition to our alkene reactant to make some sort of alkyl halide, and of course remember that's a good leaving group. We can do an elimination reaction then to get the new alkene that we want as our final product. Again, keep in mind stereochemistry, right? We want regiochemistry. We want to control where these groups are going so that we can put the functional groups where we want them. Okay, so if you look at our reactant and our product, the double bond, the two places where we have our double bonds have this carbon over here in common. So it makes sense that that's where we want our leaving group when we do our addition reaction in the first place. So ask yourself, if I want my bromine here, is that a Markovnikov or anti-Markovnikov addition across that double bond? Okay, so notice that we're adding that bromine to the less substituted of those two carbons. That's an anti-Markovnikov addition. So ask yourself, what reagents would do an anti-Markovnikov addition of HBr? Okay. Likewise, when this bromine, when we do our elimination reaction to get rid of HBr, okay, ask yourself, well, is this resulting alkene the Zaitsev or Hoffman product? And again, what reagents would you need to do that? All right, and that's it for this chapter. So tell you what, why don't I walk through that last problem just so you have the answers for it? Okay, so I pointed out that this is we're adding HBr across this double bond, and we're doing it in an anti-Markovnikov way. So we're reacting hydrobromic acid, but it's not just HBr, right? Because otherwise you would get the Markovnikov addition, and the bromine would wind up on this carbon. So instead, we have to do the radical reaction that involves using some sort of peroxide. Okay, so this peroxide will provide radicals that will cause this anti-Markovnikov addition. And again, we'll see the mechanism that causes this in a couple chapters, in chapter 11. So if you're curious and you want to read ahead, skip to chapter 11 to see how this works. But that being said, for now, just understand that having a peroxide present will do the anti-Markovnikov addition. Okay, now we want our double bond here, right? So if this is our leaving group, and these are 2 beta carbons, okay, I could form my double bond here, which is what we see, or over here. Which one is our Zaitsev product? Which one's our Hofmann product? Well, the double bond here would be tri-substituted, right? Here's 1, 2, 3 methyl groups, 3 alkyl groups attached to where that double bond would have formed. And over here, of course, it's only mono-substituted. So this is my Hofmann product, which tells me I want to use a bulky base to do this reaction. So something like potassium tert-butoxide should work. Okay, and that's how I would do this multi-step synthesis. Okay, and like I said, don't panic if this seems, like this is kind of very, very difficult. It's a new skill. It's one of these things you're going to get better at. So we'll kind of start slow, and by the time we get to chapter 12, which is where we spend an entire chapter talking about this sort of stuff, you'll have noticed that you'll have already picked up a lot of skills along the way. Okay. All right. So let's walk through the practice problems here. For this question, this is just kind of like a little paragraph problem, but if you want to answer this question, I would recommend using your Gibbs free energy equation, right? So if you have delta G is equal to delta H minus T delta S, it's not really shown here in this answer, but typically, you've got to ask yourself, what's happening to my terms? If I have delta G is equal to delta H minus T delta S, if I'm doing my addition reaction, what's delta H going to be and what's delta S going to be? We pointed out that delta H for an addition reaction is typically a negative number. Addition reactions are exothermic because you are converting a pi and sigma bond into 2 sigma bonds, right? And so you're breaking a pi bond, which is lower in energy, and forming a sigma bond, which is higher in energy. So your enthalpy term is going to be negative. This is going to be an exothermic reaction. Okay. Now, from an entropy standpoint, though, of course, our entropy is going to be decreasing, right? Because we're going from 2 reactants to 1 product. So if entropy is negative, that means our negative T delta S term is overall going to be positive. So to make this a spontaneous reaction, we want this negative term to be greater than this positive term, and in order to do that, we need to look at our temperature. If we have a lower temperature, this positive term becomes smaller. Okay. So then let's have a look at this reaction here. We are doing this at a low temperature, which we know favors the addition reaction. Okay. And we want to consider, we're adding HBr here. Again, it's just HBr. There's no peroxide or anything. So we're going to do a Markovnikov addition. But again, remember, just thinking about a rule, like, bromine's going to go to the more substituted and hydrogen's going to go to the less substituted carbon. That's not enough. You probably want to think about what's my carbocation going to look like. Okay. So if my, so depending on, the 2 places you could add your hydrogen across this double bond, ask yourself, what does the resulting carbocation look like, and are there rearrangements that can make the resulting product? Okay, they can make different products. Okay, so it turns out that while you would consider this tertiary site to be better for your bromine, it actually ends up being this one on the left, and the reason for this is that this is a benzylic position, right? We've seen that a benzylic or allylic carbocation is very stable due to resonance, and so it turns out that we actually add to the secondary position. So this is why memorizing rules isn't enough. Okay, it's a great shortcut, but you do want to think about how the mechanism itself works. And so even though you would expect a tertiary carbocation to produce the more stable product, it's actually this secondary site that's benzylic that tends to be where your bromine is going to add on. Okay. You also want to take into account that this carbon now is chiral, right? We have a benzene, we have an isopropyl group, we have a bromine, and we have a hydrogen, which is not shown. And since that carbocation is going to be flat, your bromine could add to either side. So you actually get both. You get a racemic mixture of both enantiomers. Okay. So when doing a hydration reaction, keep in mind that acid will catalyze both the addition reaction and the elimination reaction. So think about how you would drive this reaction forward. We've kind of talked about this in terms of the Chatelier's principle. Okay, so remember, since we're adding water, if we have more water present, we would drive this towards the product we're trying to make. So using a dilute acid helps. Okay. We've covered a bunch of these examples of Markovnikov and an anti-Markovnikov. Though I guess this one's kind of very specific, that we want a syn anti-Markovnikov hydration. Okay, and for Markovnikov hydration, actually, I guess with these stipulations, this actually does make the answer a little bit more specific, right? For Markovnikov hydration, we had two possibilities, right? We could use sulfuric acid, dilute sulfuric acid would do this, but it goes through a carbocation intermediate, which could possibly rearrange. So what other ways do we learn that can do a Markovnikov hydration? Well, you want to use a mercuration demercuration. So pick any asymmetrical alkene and react it with a mercuration demercuration, and that'll give you your product. For an anti-Markovnikov hydration, of course, the example that should come to mind is your hydroboration oxidation reaction. Okay, so remember your reagents for that. Okay, so there's your, here's an asymmetrical alkene, and here's our reagents for our mercuration demercuration. Okay, and so notice that we have our, out of our 2 carbons, the alcohol groups added to our more substituted one. Okay, yeah, and that's why, we've picked a reagent specifically that if we had used sulfuric acid, the resulting carbocation would have been a secondary one, and we would have seen a methyl shift that would have made our tertiary site here. And so our alcohol group would have actually added to this carbon, and we would have had an extra methyl group here. Okay, so that's why we don't use sulfuric acid for this reaction. And of course, here's our, anti-Markovnikov addition. Okay, and remember, it's a syn addition, so your alcohol group and your hydrogen add to the same side. So think about how that affects this methyl group over here. Okay, so with a halogenation reaction, is that going to be first order or second order? Okay, and then secondly, the question asks, are we doing an anti-addition versus a syn addition, right? And why? Well, the question reminds you that it is an anti-addition. Okay, and so why is that? So think about the mechanism that this reaction undergoes, and that should help jog your memory for what this looks like. So remember, the first step is you have your bromine reacting with your alkene to make a bromonium ion and to kick off that bromide leaving group. All right, so remember, there are two molecules involved there, right? Your bromine and your alkene. Okay, then your second step, of course, is where the resulting bromonium ion reacts with your bromide, which is a relatively fast step, right? Your bromonium ion is at a relatively high potential energy. It's not super stable because of that positive formal charge. So it's going to readily react with that negatively charged bromide ion. Okay, so your first step is the slow step. So ask yourself, how many molecules are involved in that? Well, that's going to be a second order, right? Because you've got your bromine and your alkene involved in that slow step. Okay, so it's first order with each of those, obviously, but second order overall. Now remember, this is also an anti-addition because that bromonium ion has one side of that alkene blocked off by that bromine. Okay, so your bromide that's coming in can only attack the opposite side. All right, here's a synthetic problem. Go ahead and try this one out. Okay. Now notice that our here's our leaving group. Okay, so if we were to do a simple elimination reaction, it seems like we would form our double bond over here. Okay, but you want to, you've got to think, okay, well, once this leaving group leaves, if we do, let's say, an E1 elimination, is there a rearrangement that would give us, allow this double bond to form? And the answer is no. So essentially, if we do a simple elimination, our double bond would be over here and not over here. So that kind of tells you that there's more than one step involved. Okay, so you're probably going to do an elimination reaction to make an alkene, but then you want to do another addition reaction to make a new alkyl halide, and then you're going to do another elimination reaction to get the alkene that you want. Okay, so take a second and try this out. Alright, so here are the steps that we see. So of course, if we do an elimination reaction here, we're going to form this double bond. They use a bulky base, but to be honest with you, since this is the only possibility, you could have used a small base, and you would have gotten the same product. This is the only place you can form that alkene. Okay, so it doesn't matter which kind of base you use. Now you want to do an addition reaction across this double bond, but you want to try and move, we're trying to move towards the left of this molecule. So going through a carbocation intermediate would be great, and to try and encourage a rearrangement. So notice that we're going to use sulfuric acid here to do our hydration addition, because we know that's going to go through a carbocation intermediate. Okay, so if you're having trouble seeing why this is the product that we form, go ahead and draw that carbocation intermediate and ask yourself, how is that going to rearrange? Okay, so remember, when you add your acid to this double bond, it adds to the less substituted carbon and puts that positive charge over here, which would make a secondary carbocation. But we could do a hydride shift, move this hydrogen, which is not shown, over to that carbon, and now we'd form a tertiary carbocation over here, which is why our alcohol group adds over there. Okay? Now we want to form the double bond over here. That is an, that's the Hoffman product we're making, right? So we want to use a bulky base, but of course, in order to use a bulky base here, we would need a better leaving group than an alcohol, and we can't use an acid, of course. So we're going to use a, we need to use tosyl chloride and pyridine to tosylate this alcohol group. Okay, convert into a tosyl leaving group, and then we can do our Hoffman elimination using our bulky base to make the product we see. Okay. So, just to summarize, I had this slide at the beginning of the chapter. Here are all the addition reactions we've seen. Okay, and of course, the sections here will remind you if you want to do further reading on each of these. And you want to read up on the different considerations for regiochemistry, for stereochemistry, and so on. Here are the relevant chapter selections for this. Okay. Now, in your textbook, we have what we call reaction wheels. All of the reactions we've learned today with our addition reactions are summarized in this diagram. Okay, so both the names of them, the reagents we use, just kind of the stereochemistry and regiochemistry considerations, all of that is in this diagram. So this might be a good thing to have on hand when you're studying for a quiz or exam. It's essentially like the equivalent of having like one giant flashcard to help you memorize these different reagents and so on. Okay, so this might not be a bad study aid to have on hand. Okay, and so that's the end of this chapter. Let me know if you have any questions.